we've seen all of this. Yeah. So, I think somebody had just asked at the beginning of this session that how do we choose the topmost variable if I have to construct an ROBDD? So, in fact, this is not an easy problem because given the same function, here is one ordering of variables and here is another ordering of variables. And you can see that the sizes of the ROBDDs are very, very different. Okay. And if you stare at this function for a moment, perhaps it's also clear why it is so. Because in some sense, if I know the value of x1 and x2 are both true, then I don't need to know the values of these things. So if I could keep x1 and x2 together, perhaps, or close by, perhaps that would be helpful. Whereas here, this is like maximally separating out x1 and x2 because it's interleaving x1, x3, x5, and then x2, x4, x6. Okay, so it's a special pathological case function, but it just illustrates that when you're choosing the variable order, perhaps it is first of all that the size of the ROBDD can differ, and perhaps it is best to keep correlated variables or variables that might affect the value of the function, working together close by than far apart. Okay. So it can be extremely sensitive to variable ordering, and in fact, a generalization of the function that I just showed you can be shown to have linear number of vertices in the ROBDD, so linear size for a particular ordering and exponential size for another ordering. So that is how much different it can be. Whereas there are other functions for which no matter what order you choose, you're going to get the same size. Okay? So this is so determining the and in particular, the multiplication function, which means if I take two n-bit integers and if I try to represent the Boolean function that represents the different bits of the product of these two n-bit integers, then particularly the middle bit, the nth bit of two n-bit, the nth bit of the 2n-bit product of two n-bit numbers, that is indeed known to be a particularly tough case in the sense that no matter what variable ordering you use, you'll get exponential size. And determining the best variable order is actually NP complete. So people really use different kinds of static and dynamic ordering. So while I had something about static ordering, let me not go through it in detail, but let's just say that typically in hardware, you'll have control variables and you'll have data variables. So if for whatever reason you have a ROBDD which have both control and data together, it's perhaps best to, because the data variables, can be, depending on the width of your data path, it can be too many. So typically it's a good idea to keep the control variables closer to the roots and then related variables closer to each other and so on. Okay. So for example, A greater than B, if I sort of keep the bits interleaved like this, sorry, this should have been A31 less than B31, then A30 less than B30, A1 less than B1, right? Because a comparison between these two things can automatically tell me whether A is greater than B. If A31 is 1 and B31 is 0, that's it. I don't need to look at the other things. So basically you can use some insights into what function you're trying to represent to order the variables, but nevertheless finding the best variable order is difficult. And then people use what are called dynamic ordering. In the interest of time, let me not go into this. I will make the slides available. So this is really saying that this is actually quite useful, but it's also quite expensive in the sense that as you're building the BDD, right, you might realize that you have crossed a certain size budget. You are occupying too much memory space. So at that point, you can do a sort of expensive operation to sort of figure out what would have been a better order than the current order that you have, and then figure out that order and then maybe reconstruct the BDDs according to this new order. So really what people do is they don't figure out a completely new order. They take the existing order, look at a small part of it, like a peephole optimization, and then they try to see if something can be reordered there. So for example, this could be part of a BDD. There are other BDDs below and above, other BDD nodes below and above. So here, if I want to reorder A and B, then this can become something like this. But, let's not spend too much time on this. This is just to show that There are techniques that try to do this on the fly as and when needed, as opposed to doing it statically. And this is sometimes very useful when you're really dealing with large functions, but this is also expensive. Okay, so uh, ROBDD packages, in fact, we are going to use this in this afternoon in our hands-on session as part of the ABC package. So they are, quite mature, and they use lots of internal bookkeeping. Once again, let me not get into this in the interests of time, because there are a lot of other topics I want to cover. But this is just saying the internals of ROBDD packages have, all the software caches. There are hash tables. There are sharing data structures, all kinds of things. And for example, they do things like this is really cool. So remember, we said that complementing an ROBDD is easy. You just have to flip uh, the leaves, the 0 and 1 leaves. But you realize that this really can't be done if you have an ROBDD manager in which several ROBDDs are being maintained. So there is, of course, one leaf called 0 and there is one leaf called 1. And all the ROBDDs are eventually, leading down to that one leaf called 0 and one leaf called 1. And if you wanted to complement one particular function, if you go and flip this, then all your functions have been flipped, right? Because everybody was sharing this leaf. So, so what they do is they use something called complement edges. Okay, so a complement edge means that, so instead of flipping the leaves, they say they put something like this, saying that, well, if you're coming from here to here, right? So remember, this means that if x1 is true, then I should take the function at x2, the function represented by x2. But here this means if x1 is true, then take the negation of the function represented at x2. And then whatever is above, that is going to take the negation of the function represented by x1, and so on. So for example, the same function that is represented by this, which is this, if you are using complement edges, you can represent it much more compactly. And of course, here complementing is really order 1 time and space, right? You want to complement ability, just put a bubble on the incoming edge. Okay. So and then they have garbage collection, to make sure that the memory management happens properly. So it's a very sophisticated packages. And then there are things called multi-terminal BDDs, edge-valued BDDs, binary moment diagrams. This was particularly invented to take care of multiplication. And of course, it's useful for other purposes also. So uh, as I said, the middle bit of the product, no matter what BDD or what variable ordering you use, is exponential if you construct a BDD, but here it can be made linear size. Then there are things called zero suppressed BDDs. So where basically the zero leaf is not there. If there was a path going down to the zero leaf, you just don't have the path. So what it means is that, if at a particular node you have no way to go out, you mean that it would really have been zero. And this is also known to be canonical zero suppressed BDD. So there is an entire ecosystem out there, and very, very useful data structures have proven their worth over a long period of time. Then people also try to use these things called partitioned ROBDDs. But in the interest of time, let me just skip these things and let me come to the next data structure that, these are there in the slides. I will make the slides available. You can look at them. So my intent here is to make you a bit familiar with the core ideas of the data structures so that you can appreciate them when we see in the hands-on exercises, and then see how we can use them for the different kinds of things. I'm still talking about how to represent functions, right? We still have to come to how to use this for verification. So that is why I'm sort of glossing over the parts that are very implementation specific. Okay, so the next data structure that we're going to see for representing functions are called And-Inverter graphs. And this is really saying that we know that and not is functionally complete, right? You can represent any function using and not. And then because and is an associative operator, so you can just have two input ands. Any n input and can be built as a tree of two input ands. So therefore, this suggests that we can represent any Boolean function as a graph in which all the nodes are two input AND nodes. So the in degree is always 2. The out degree can be arbitrary. And there are bubbles on the edges which represent um, inversions, right? So for example, this is how you would represent A or B, right? So it's saying negation A and negation B and the negation of that, okay? And this is how you would represent A XOR B. This is how you would represent if then else of C A B, more complicated function, but it just shows that this is yet another way of representing Boolean functions. Okay, now we have already sort of seen BDDs, ROBDDs for representing Boolean functions. So why are we trying to look? And I have already waxed eloquent about how great ROBDDs are. So why are we looking at this other thing at all? And it is because of that one problem that I told you, that sometimes BDDs can just blow up in size, and sometimes it depends on the variable order. So you can put in some effort in finding a good variable order. But there are other functions like the middle bit of the product of two numbers, where no matter what order you use, there's an exponential blow up. So we want to see whether there are alternative data structures where we can still represent Boolean functions without the exponential blow up. But once again, as with everything in life, there are no free lunches. So if you want to get compact representations where BDDs are failing, you have to give up some of the nice properties about BDDs. The question is that maybe it's still worth doing it, because maybe we give up some nice properties of BDDs, but we still retain some other properties, and maybe we have some other newer properties. And so that's why we are looking at these And-Inverter graphs. This is also another data structure that has stood the test of time. We'll see it in action shortly. So the first thing that we give up when we go from BDDs, ROBDDs to AIGs are that they're non-canonical. I can have two different looking structures, And-Inverter graphs. So these are graphs of ANDs and inverters, but I can have two different AIGs that represent the same function. And here, for example, I have represented A and B and C and D using two different AIGs. Okay. The size of the AIG is typically measured in terms of number of AND gates, because that's kind of the main operator you have. The depth is usually the longest path from the root to a leaf. And it turns out that although these are non-canonical, but if you want to build pretty much any of the Boolean operators you can think of, you can actually efficiently build such circuits. So, for example, here is an n-input XOR that I want to build. So all that I do is, I'm going to build an input XOR as a chain of XORs, two input XORs. So here is the pattern for a two input XOR, which we saw in an earlier slide, right? So I'm going to use that pattern, and then I'm going to just repeat that pattern. And because I have the ability to connect the output of this node to the inputs of some other nodes, so I can just keep connecting them like this, right? So I can replace each gate, right? Basically, I can build my circuit in terms of AND, NOT, OR, NAND, XOR, whatever gates, and then I can just syntactically replace each gate by the corresponding AIG equivalent. And whenever I in doing so, I might sometimes end up in a situation where I have two bubbles along an edge, right? Maybe there was a bubble coming out from the output of a gate, and maybe at the there's another gate that I'm sort of coupling up with this, so that bubble is there on the input of that gate. So of course, if an edge has two bubbles, you can just remove both the bubbles, right? The bubbles are inversions. So two inversions is the same as no inversion. So it can be exponentially more succinct than CNF or DNF. For example, an n-input XOR gate, whether CNF or DNF will be exponentially large, but this can be linear. And it can be exponentially more succinct than BDDs. For example, that specific case that we were talking about, n-bit integer multiplier, the middle bit, and we can of course represent it. I mean, we know how to design a circuit which represents the middle bit, and that circuit is at most quadratic in size. This is take the usual high school multiplication algorithm. And so if that circuit is quadratic in size in terms of AND or NOT gates, then I can certainly get an AIG, which is the same size in terms of and or not gates. And in fact, in this particular case, I think we can do it even linear in n. So, but certainly quadratic in n. I have to check this whether I think it is linear in n. Yeah. Okay. So, so it looks like, the main thing that was bothering us with ROBDDs was that the size could blow up. Finding the best variable order was difficult. That we have kind of tamed. But now, the price that we are now paying is that tautology checking or satisfiability checking, there it was just, I could look at the BDD and say whether it is satisfiable, whether it's a tautology, whether it's unsatisfiable. Here, I can't do that. Why? Because this is not a canonical representation. If it was a canonical representation, I could have done that. But this is not a canonical representation, so I really will have to check satisfiability of the function represented by the output of the AIG. Now, it turns out that, of course, satisfiability checking is hard in the sense that it's NP complete. But of course, I'm sure, you have been told that there are, in fact, we'll see these in action today in the hands-on session, that today's SAT solvers are very, very powerful. I mean, they can literally crunch millions of variables, hundreds of thousands of clauses, very efficiently, even on a laptop. So, so satisfiability checking, while it's complexity-wise bad, but in practice, it may not be that bad. But for all of the satisfiability solvers will really take in a CNF formula, a conjunctive normal form formula. All standard satisfiability checkers will do that. But our AIG is not CNF. So how do we convert from CNF to from AIG to CNF? So we'll see that there's also a very, very efficient way to do this called Cyton encoding. And the fact that there is this very uniform structure, right? That I'm only talking about AND gates and inverters and nothing else. So this is also useful in a particular line of SAT solving, which is called circuit-based SAT solving, where you try to identify circuit structures with whether the output of that circuit will be, false or satisfiable or unsatisfiable. So there are these advantages. Okay. Now let's see. Can we do similar kinds of operations like what we had done earlier with ROBDDs? So negation is trivial, just add a bubble, right? It's similar to the complemented edges in ROBDD packages, right? So a binary or a ternary Boolean operation is once again easy. Like if these are already your existing AIGs representing F and G, if you want to do F op G, you just put the AIG, which is for the op operator, and just plug in the inputs over here. That's it, right? For example, if op is OR, then this operator is this. Okay, easy. Compose. So remember, we have bubbles at some places, inside our AIG. So we have to just take care of that. So for example, if I'm, remember what was compose? Compose was saying that you have a function f, which depends on some input v. And in place of the input v, you want to plug in the function h. You want to plug in the output of the function h. H is another function. So if I'm trying to compose negation, the function negation g at the input variable v with the function h. So this is not hard to see that, you have a function and you have the function g, and then you have a little bubble at the output of it. And you want to say that for this whole thing at the input v, I want to plug in h. So this is the same as saying, okay, plug in h at the input v of the circuit for g and just negate its output, right? So what this allows you to do is, this is just showing that can we come up with a recursive formulation. So I have sort of this g here, I have removed one operator from there. From negation g, I now have to work with g. What about compose g1 and g2? This is very simple. If g1 and g2 is a function, and if the variable v has to be replaced with the function h, do that in each of g1 and g2. Okay. So, and this is how you sort of, and remember, these are the only two operators we have, not and and. Right? So if I can figure out how to do something with not, how to do something with and, that's it. I don't need anything more, right? And when do I terminate? So termination is like, if I finally reached a leaf, at the leaf I have the variables, and if I'm trying to say, okay, compose v for the function v, which depends on the variable v, compose the function h at the variable v, this just means you have h. And similarly, if you have reached a variable u and you're saying compose at v the function h, then there is no dependence of u on v, because this is just a leaf variable. So you just get u itself. Okay. So these are all easy operations on AIGs. Satisfiability, tautology, contradiction, these are, of course, we need to call SAT solvers. So if you look at the complexity of operations, once again, by f here, I will mean a function and the AIG representing it. And here the size, here by the size of a graph, I mean the size of the AIG representing the graph. So complementation is very easy. Binary Boolean operations, ternary Boolean operations, very easy. IT is easy. Compose is, as I said, you just keep coming down to the leaf, and by that time you're done. So these are all very nice properties of AIGs. But satisfy one is NP complete. Whether there's one satisfying assignment, at least one satisfying assignment. Model counting, we have not simplified anything at all, so it is still sharply complete. Restricting is also very straightforward, because what does restricting do? It says set V to 0. So you take the leaf, set it to 0, and that's it. You have the circuit. Or take the leaf, set it to 1. Okay. So all of this is very nice. So if you take AIGs, which looks like are interesting data structure, at least takes care of some of the size issues that we had earlier. And if you combine them with powerful modern SAT solvers, then this really becomes a scalable approach to large industrial scale problems. And in fact, it is used in industrial scale problems. Okay. So now I just want to illustrate, how an AIG operation happens. So here I have two functions, f and h, and here there is a variable v, right? So this is a function f that depends on the variable v. Notice that the function h also depends on the variable v, right? So how do I do compose fvh, which means I would like to find out the function that results if I look at f, and at its input v, I plug in the function h. Now clearly I can't take h from here and plug in there, because then I have destroyed the function h, right? I mean, I have introduced a cycle. That's not what I meant, right? So, while for normal circuits, I mean, if f and h did not share any variable, I can do this. I can just, then it's as easy as that. Just take the output of h and feed it to the input of f. But of course, if this variable v is going and, feeding some other functions also, then I still can't do it, because by changing this, by replacing this with something else, those other functions would also get affected. So in general, you can't just take the output of h and plug it into v and connect it to v. But we still need a function f changed by whatever I should get if I replace the input v by the function h, right? So this looks like an interesting thing to do. And let's see how we'll do that. And this is the whole reason I wanted to show the animation. Okay, so function f is negation G1 and G2, right? Here you can see negation G1 and G2. So I will say, okay, recursively, I will first do this composition on negation G1, VH, and then I will do it on G2, right? So we'll look at the G2 part later. Okay, so now how do I do it for negation G1? What we said earlier is that, if you look at the negation G1 function, and if you want to replace V by something, that's the same as looking at the G1 function, replacing V by something, and then negating the output. Now, okay, what is G1 made of? G1 is made of U and negation V. So I will say compose UVH and compose negation VVH. And of course, that other part is still remaining. We have to still do it. Now, what is compose UVH? U is a leaf already and V is another leaf. So what does it mean to say that in this function, I want to replace this variable by something? You'll get back the same U. So I'm done here. And what is compose negation V with VH? So once again, I'll push the compose inside the negation. So it's negation compose VVH. And now what is this? This is saying I have a function V, which depends only on the variable V, of course. And in that function V, I want to replace the variable V by the function H. So what will I get? I'll just get H straight away, right? So I get negation U and negation H. And how do I represent that? I say, okay, take U from here, take H from here, right? So remember, this was H. So negation H is before the bubble. So take U, take negation H, and them up, and then put a bubble on the top. Okay. So this part is completely done by adding one AND node over here. Now we go to the other part. Sorry. So we say compose G2VH. So here is G2. I have to do right. So that because this was F was negation G1 and G2. So I have to now do G2VH. Okay, now what is G2? G2 is V and negation W. So I have to say VVH and negation WVH. Once again, VVH becomes the same as H, and negation WVH becomes negation compose WVH. And once again, W is independent from V. So this just becomes W. So it is H and negation W. So once again, I take H from here, right? So H is really after this inversion. So if I pull out an edge from this part, so okay, maybe I should say here, the fan out always happens from the output of the AND gate. The fan out never happens from the output of a bubble. These bubbles are just annotations on the edges. So I have to fan out from here, but because I need H, I have to replicate that bubble there. And there is negation W. So W, let's negate it, AND it up, and that is H and negation W. And finally, I have to AND these two up, right? So I take these two things, AND them up, and that is the result of compose FVH. Notice something remarkable, that I did not actually take the output of H and plug it into V, because that would have created a cycle. However, I have been able to generate a function which would give me the result of if I had took F separately and if I had taken H separately and plugged in H at the input of F, at the input V of F, right? But here the way I have done it is I have just done it, by recursively descending into the structure, and I still have F, I still have H. The input V is not disturbed at all. So if any other function was sharing this input, it can continue to share it. I have my new node which represents compose FVH, and I just needed to add 3 nodes to get this done. Okay. So this is the nice part about AIGs, that you can actually do a lot of operations very efficiently. Okay. Okay. Now, AIGs are not canonical, but when you construct AIGs, you actually take care. I mean, we will see this happening in the hands-on session, that you actually do a lot of simplifications that can just be done. These are like peephole optimizations in a compiler, right? You just see a structure locally and you realize, okay, I can simplify it, and you simplify it. So I have written a small sampling of simple rewrite rules that are always in action whenever you're dealing with AIGs, right? If you have an AND node and both of them are coming from another node, just use that node directly. One of them is inverted, this should have been, yeah. So it is false. False means 1, which is inverted then. So it is false. 2 bubbles, change it out. Something ended with 1, you can replace it. Something ended with 0 is 0. And then you can also do things like this. So here, what is happening is that, this guy is the AND of this and this, but this is the AND of this and this as well. So this guy is the AND of this, this, and this. But then why do I keep it twice? So I sort of separate it out over here and keep it like this. And similarly, this is another one where I'm saying that it's the AND of this, this, and the negation of this, right? But then I know that this is going to become false. So it will look at this pattern and I can just set it to false. So there are a lot of these very, very local, if you say I'm only going to look at one AIG node and what is happening at its input and what is happening at its output, I'm only going to maybe at the input, there can only be 2 things. At the output, you can say, okay, I'll restrict myself to looking at only 2 things at a time. So there are only so many structures, there are only so many patterns that you can see over here. Just put in rewrite simplification rules for all of them. And these are very easy to match and do the rewriting as you're building the AIGs. Okay. So AIG-based tools literally have tens of such rewrite rules, and is really a peephole optimization, for example, which will look at little sub-circuits where maybe up to 4 inputs, up to 3 inputs, and these are very, very effective in reducing AIG sizes. Okay. Now, there's something interesting that happens when you do such size reducing rewrite rules. And here is one illustration of that. So, this is a representation of this function A or B, B or C, and then the AND of these two. And because this is equivalent to this, maybe you can apply a local, pattern match to sort of say, okay, this is really A and C or B. But if the same pattern was present and then there were other things also pointing to here, then you can't really get rid of these nodes because there were other things which were pointing to here. They needed the functionality of these nodes, right? So you have to keep those things as they are, plus you will end up generating this. So it can actually end up increasing the overall size. Although if you just look at the function that you're trying to optimize, that sub function you're trying to optimize, that has reduced, right? So locally size reducing can be globally size increasing. So you have to apply these carefully. There are lots of heuristics to do that. Okay. Now this is something, another technique, which is a very simple technique, but very, very effective. That, just like for ROBDDs, we would not like to have two AIG nodes representing the same function. But since we don't have canonical representations of the functions, we cannot exactly be sure that if two nodes are representing the same function or not. We'll have to do some kind of SAT call to figure that out, equivalence check. But we can do something slightly less expensive, and which is also going to be effective a lot of times. So ideally, we would not like to have two nodes representing the same function, right? And for example, here, I think R and S both represent P and R is P and Q, and S is also P and Q. Okay. Yeah, I think it's P and Q, P and C really, right? R is P and C, S is also P and C. So for these two nodes, actually, it's kind of easy to detect that they're doing the same thing because both of their inputs were coming exactly from the same nodes, right? So whenever I have something like this, that I have two AIG nodes and all their inputs are the same, then I know that they're certainly representing the same thing, and so I can collapse them. So this is what is called structural hashing, that if two nodes have both the inputs the same, remember our nodes have only two inputs, then we can just collapse them, right? So we can maintain a hash table with the two inputs I1 and I2 as key and a pointer to the node representing I1 and I2 as value. And then whenever I have the same hash, I know that I should use the same node. I should not create a separate node. Okay. And of course, we make sure that we don't have nodes with constant inputs or a single input. Now, structural hashing can be particularly useful, because this thing can propagate. Once you have merged two nodes, two other nodes which earlier could not be merged can be merged, and so on, right? So there is this command, in this AIG tool that we're going to be using called strash, which means structural hash. And what it does is, before it creates any new node, it checks whether the hash table has either this or this. It can also impose an ordering on the nodes and check for this, if that's how it is stored in the hash table. If it is already present in the hash table, use it. Otherwise, you create a new node and make a new entry in the hash table. Okay, this is how the library operates. So for example, in this case, these two would get merged and we would have only the node R, and wherever S was leading to, R will now lead to there. Okay. Now, even after we use this trash and rewrite, and for example, sorry, yeah, right. And for example, now that this circuit has changed to this, it is perhaps worthwhile asking, are these two nodes the same? I mean, they don't look like they're the same because they're coming from two different things, but then maybe we can ask, well, are these the same? they don't look the same because their inputs are different. But we can sort of ask that, are these two nodes really representing the same function? I mean, structurally, they don't appear to represent the same function, but are they representing the same function semantically, right? So this is what we're saying, that even after using strash and rewrite, the AIG may contain nodes that represent the same or complemented functions, and that's exactly what we were trying to show earlier. And in this case, actually, P represents A XOR B, Q represents A XNOR B, and so if you complement it, then you once again have these two nodes representing the same function. Okay, but so it will be desirable to merge P and maybe negation Q together and use bubbles on outgoing edges to denote the complementation. But strash does not help. So what we can do is we can take these two nodes and we can ask, is P equivalent to Q or is P equivalent to negation Q? Because any one of these satisfying allows us to collapse. It doesn't have to be equivalent, right? It can be even negation. Because even if it is negation, I can collapse them, and wherever I was using Q, I could use an edge with a bubble on it. Okay, so can I have this or can I have this? And of course, this is a tautology or SAT check. And if yes, we can merge and use bubbles appropriately. So this is what is called a functionally reduced AIG, also called FRAG. This operation, functionally reducing the AIG, is called FRAG. So what is done is that you do not want two nodes to represent the same or complemented function. And so for every pair of UV of nodes, including the constant node 1, remember there is no zero node because 0 is obtained by complementing 1. You check if this is a tautology and you check if this is a tautology. And once you have figured out if one of them is a tautology, you use simplification rules and structural hashing all throughout. Now, this sounds like a good idea in principle, but of course, this will require a SAT call. And if I have to do this for every pair of nodes in an AIG, then there are just way too many SAT calls that are going to be needed. And so that is not going to work. Okay. So here in this case, for example, we could do a FRAG operation and determine that P and Q are the negations of each other, in which case Q would get merged with P. And so I'll just have P, and wherever Q was going, right, there was this arrow going here with a bubble here. So instead of this arrow, I'll have an arrow from here with a bubble, right? Because Q was negation P. But then I'll see two bubbles over here. So I'll just get rid of them. And now you see that these two nodes have the same inputs, right? Both are coming from P and C. So, oops, one second. Yeah. Okay. So yeah. So now I can do strash here, and this will give rise to just this node, right? There's a single node for both of these, but if there's a single node for both of these, then G has both its inputs coming from the same node. So I don't need G at all. It is like R and R, so it is R really. And so when I rewrite it, that's what I get finally, right? So I started off from an AIG which was looking much bigger, much more complicated, but then I used strash, rewrite, FRAG in some sequence, and this is what I got finally. And this is still representing all the functions that were present in the earlier AIG. Okay, all the functions that is both F and G that were being represented by the earlier AIG. Okay, so I mean, this process of fragging is involving SAT calls, but we must be careful about the fact that even by doing these SAT calls, we are actually not getting a canonical representation. Canonical means there is only one way to represent a function. That's what ROBDDs do. For example, if I take these two, if I take these two AIGs, each of these AIGs is frag reduced. I mean, you can't reduce this AIG further by fragging. There are no two nodes here which are equivalent. You can't reduce this AIG further by fragging. There are no two nodes which are equivalent. So this is a frag reduced and strash reduced AIG. This is also a frag reduced and strash reduced AIG. They represent the same function, but they don't look the same. So doing a Frege reduction does not mean that you're canonicalizing. You're getting a unique representation from for the function. Okay. However, AIGs are what are called semi-canonical. And what does this mean? It means that if you are within the same AIG manager, I mean, if both this and this were within the same AIG manager, then these two nodes would get merged. These two nodes would get merged, right? So within the same AIG manager, if you do Freging, then there is only one representation for a function, but it doesn't mean that that's the only way to represent that function. Okay. And of course, Freging can be expensive. As I said, if you want to do it for every pair of nodes, it's actually out of the question. It's not practical. So what is typically done in practice is that you restrict the pairs of nodes on which SAT solver is called, and you Frege infrequently. And there's a very clever way in which this restriction is done. Basically, what you do is you pick sufficiently many random 0-1 input vectors and you feed it to your Frege, right? So basically, you take a Frege like whatever you had, maybe over here, this Frege, and or actually let's look at this Frege over here, right? This one that we had. So I'll take this Frege and then I'll put some random values over here. In general, there may be large number of variables. I'll put some random 0-1 vectors, and I will evaluate this Frege for each of those random 0-1 vectors. Evaluation is very easy, right? It's just ands and nots in linear time I can evaluate. So I'll present some random vectors here at the inputs, and I'll evaluate the Frege. And in each evaluation, I will check whether a node which nodes have evaluated to 0 and which nodes have evaluated to 1. Now, if in any evaluation, a node has evaluated to 0 and another node has evaluated to 1, these two nodes cannot be semantically equivalent because there is at least one input for which they are differing. They can be semantically complement, but they cannot be equivalent. And similarly, if two nodes have evaluated to the same thing on a particular input, they can be semantically equivalent, but they cannot be semantically complement. And now suppose I figure out that, okay, these two nodes are, I'm just randomly picking two nodes. Suppose I figure out that for one input, these two nodes are both evaluating to the same thing. Maybe both are evaluating to 0 and these two are both evaluating to 1. Then I know that, well, I don't need to do the complement check for these two nodes, and I don't need to do the complement check for these two nodes. I don't need to do the equivalence check for these two nodes, and I don't need to do the equivalence check for these two nodes. So a lot of checks are automatically getting cancelled out, made redundant just by simulating one random vector. And now if I put the next random vector, maybe for that, these two nodes turn out to be different. So now I know that I don't need to check them for equivalence either, right? So this is exactly the technique that is used to make this Freging, practical. That initially you put everything in one partition, and then sufficiently many times you pick a random vector and evaluate all nodes, and you refine each partition. The nodes that evaluate to 0 and the nodes evaluating to 1. You sort of say, okay, for these I need to, if both of them evaluate to the same thing, you should not try to do a SAT check that they're complements of each other. If both of them evaluated to different things, you should not try to do a SAT check that they're equivalent to each other. And as you're picking different random vectors, these partitions start getting refining. And finally, only in the in the small refined partitions that remain, you need to do these final SAT checks. Okay, so the number of SAT checks can be drastically reduced by doing this very simple random simulation based filtering. Okay, so and then as I said, finally, if you want to check if some node is equivalent, you have to ask whether the A and negation B or B and negation A is satisfiable. So you have to make a SAT solver call, and if so, if this is unsatisfiable, then you know that they're equivalent, you can merge them. And if they are satisfiable, then you can, the satisfying assignment will give you an assignment that distinguishes A and B, and perhaps that will also distinguish some of the other things that were there in A and B, and then you go ahead and sort of do this. So this is very fast heuristics, very simple-minded heuristics, but very effective heuristics. Okay, now yeah, I think I should kind of try to wind down the AIG part here. So there are other operations, and so these are really useful for synthesis, verification, and all kinds of things. And there are other operations that you can use on AIGs. You can balance the depth along, basically try to make the paths from the root to the leaves more or less at the same length. So this is useful for optimizing delays. You can refactor, which means you can introduce a cut in the AIG and then express the function of an AIG node in terms of the cuts. And then you can separately go and optimize the functions at the cuts. You can collapse. So there are all kinds of operations that you can do. Okay. Now, yeah, let me just spend a couple of minutes on this part that, it looks like SAT solver calls are going to be quite useful when I'm using AIGs. So how do I build a CNF instance given an AIG, right? So CNF, all of you know, so I don't need to go into this. So our problem now is, given an AIG for F, how do I generate a CNF for F, without blowing up too much? I mean, if I start from, if I sort of apply this, distributivity rules, then it can indeed blow up because it is known. But for example, for XOR gates, it is known that whether you convert to CNF or DNF, it's going to blow up exponentially. So we don't want to do that. We have a nice small AIG, and we just wanted to do a check whether something is satisfiable or not. We don't want to blow up in trying to build the CNF formula before feeding to the solver. So this is done by doing what is called Cyton encoding. So what we do is, given an AIG for F, so was Cyton encoding done as part of Monday's lecture? Shubhajit, can you? I didn't notice it.
I don't think so. Maybe not.
Okay. So then let me quickly cover it. So basically, we are given an AIG for F, and we want to get a CNF formula. Ideally, that should be equivalent to F, but remember, we are only interested in knowing, is F satisfiable or not. So we will say that, well, we will get a formula G, which may not be equivalent to F, but is closely related to F, in the sense that it is equisatisfiable, which means if F is satisfiable, G will also be satisfiable. If F is unsatisfiable, G will also be unsatisfiable. Okay. So equisatisfiability is not the same as equivalence. For example, A or B is equisatisfiable with C and D. Both formulas are satisfiable. So they are equisatisfiable, but they're clearly not equivalent. Right? So this Cyton encoding is basically what is used to take an arbitrary Boolean circuit, actually, AIG just being a special case of that, and give you another formula G, which is linear in the size of F, which is in CNF, and it will be equisatisfiable to F. Okay. So we want this. So given the AIG F, I want to generate an equisatisfiable formula G, such that G is in CNF. Size of G is linear in the size of F, the size of the AIG, and they're equisatisfiable. Not only they're equisatisfiable, we have a much stronger property here, that if you find a satisfying assignment for F, then this will give a unique satisfying assignment for G. And if you find a satisfying assignment for G, that will give a unique satisfying assignment for F. So the satisfying assignments for F and G are in bijection with each other. Okay. And this is actually widely used in the SAT solving context. So let's quickly see how this works through an illustration. Right. So we are given this Boolean circuit F, which is actually A XOR B and C. And we want to convert this to a CNF formula, which is equisatisfiable to this. It may not be equivalent to this, but if this formula is satisfiable, the other formula will also be satisfiable, and vice versa. And remember, we are just trying to show this illustration on a very small AIG. You can do this for a very large AIG as well. The procedure is actually just linear. Okay, so the first thing that we're going to do is we're going to associate some new variables with the output of each gate. F is already associated with the output of this gate, so I don't need to use a new variable. For these, I associate some new variables. And then for each Boolean gate, in this case, we have just AND gates, we will generate a formula that expresses its output in terms of its inputs. Okay. So for example, I will say T1 is negation A and negation B. T2 is A and B. T3 is negation T1 and negation T2. So I'm just expressing each gate in terms of its immediate inputs, the output of each gate in terms of its immediate inputs. And finally, F is T3 and C. Okay. And then remember, we are just talking about two input AND gates. So each of these outputs are expressed in terms of two variables. So these are functions of two variables. And what kind of functions can these be? I mean, there can just be AND over here, and maybe some of these are negated, some of these are not negated, right? So, we can just write down, I mean, this kind of Boolean function, we can write down as a CNF formula of a fixed size, right? So for example, if I have to say T1 is negation A and negation B, I can just write it down in CNF completely like this. And because this is just a two input gate, I know that this formula cannot be very large. It's of constant size actually, right? I mean, because there are only two inputs to this gate, so there are only so many variations that can happen. So this formula is of constant size. And this formula, this red formula is semantically equivalent to this formula. So I'll do that for all the green, blue, and black. And then I'll finally say, AND up all of these, right? So this formula, and this formula, and this formula, and this formula. And finally, I want to say that F is also true, right? So now you think about it. What did I do? I took this circuit. For each gate, I wrote out a constant sized formula, and I ANDed all of them, and I finally ANDed the output of this circuit. And I'm claiming that this is a function G which is equisatisfiable to F, which means if there is a way to satisfy F, there is a way to satisfy this function, and vice versa, right? And this is not very hard to see. So this is the function G, and that's the function F. And this is not very hard to see because, what have I done? I have just represented the outputs of each of these gates explicitly. So if I find a satisfying assignment for G, it will actually give me values for all the inputs and the outputs of the gates. And finally, it will also set F to true because I have conjuncted F at the end, right? So a satisfying assignment for G will actually give me the values of the inputs, the values of the intermediate nodes, and the value of the output, and specifically set the output to true, which means it will give me a satisfying assignment of the original formula, right? And similarly, if I have a satisfying assignment of the original formula, I can put that assignment at the inputs, find out what these intermediate variables will evaluate to, and use those values to get a satisfying assignment for G. That's all, right? So if I have a satisfying assignment for F, I evaluate all the gate outputs for the satisfying assignment, and that gives me this satisfying assignment for T1, T2, T3 to use in G. And similarly, if I get a satisfying assignment for G, then I can just take the part that's coming that relates only to the inputs, and that will give me the satisfying assignment for F. And note that this is in CNF because for each little gate here, I have written out a CNF formula, and when I conjoin them together, when I AND them together, that's still CNF. And finally, I'm ANDing a literal, so it's still CNF. So this is a linear time translation of any formula coming from any Boolean circuit, as long as it has a fixed or bounded number of inputs, to a CNF formula that's not equivalent to it. Actually, this formula has variables which the original formula did not have. But it is equisatisfiable, and there is a bijection between the satisfying assignments. So, okay, let me stop this presentation here. I have overshot a little bit, but there are several tools that are available there. In fact, we are going to be using in the hands-on session this tool called ABC. But let me not go further with this. And this is what I want to talk about now, that once you know these interesting representations for Boolean functions, you can actually use them for combinational equivalence checking, sequential equivalence checking, symbolic and bounded model checking. And these are the three topics I want to talk about. Okay. So let me stop this presentation here. If there are any questions, please ask them. We are actually now going to see usage of these in these three problems: combinational equivalence checking, sequential equivalence checking, and symbolic and bounded model checking. I mean, of course, given the time constraints, we'll be able to see these, only at a slightly high level, but hopefully it will make sense.